Okay, let me say something about our second assignment, okay? And when I ask you to collect all this data, okay, ask your friends is about the, do not assess those new babies or those from kindergarten, which are really different groups, okay? Just, I think you can collect all this from 20 to 40 ages. Okay, that'll be fine. Okay, do not collect those babies in the garden. That would be, really different. Yes, group. So, I mean, if you have a friends like me, I'm very short. I'm just about 150. Okay, so my wider should be 0. Okay, and so you're talking about those who are shorter than that, 140 something. Well, maybe choose another. Okay, since we need a variable which is higher, taller than 150, 5 feet. Okay, if you want to really collect the data, we can make it this way too. Okay, why don't you pick the original? Okay, and I think we can play some games too. Okay, pick the original one, and the other variable, the other y variable is minus 150. Okay, then you can run the regression both. I mean, with one with original height, the other one is above 5 feet. Okay, then see any difference from the result. I think that's interesting, right? Right? So that will answer your question about why do we need to collect the data which is above 5 feet. Is there any difference that we define the y variables in different way? That how does that affect the coefficient of the x variable? So that's interesting, right? So why don't we, just add one more, just for every step, okay? I mean, you do the 2 parts. One is for original y variables without subtracting 150. The other one is really subtract 150. Then you can compare the result. I think this is very good exercise for you to do and understand it after you really practicing. Okay? All right? Okay. So this is our assignment. Okay? Now let's finish chapter 2. I think I covered up to 2.4 last week. Let me continue doing all this explanation and which you all remember that we explained all this R square. You all remember that? And when you had it, so let me just review what we have learned for coefficient of determination, which is R squared. So how do we calculate the R squared? What's the definition of R squared? It's the ratio of ESS to TSS. Remember what's the ESS? ESS, the variation by the model. And the other parts RSS, okay? RSS is the residual part, error term part, okay? So Y is the TSS, is the total variation of the Y. Okay, according to the regression analysis, the TSS can be decomposed into two parts. One is explained by the model, which is the ESS. The other one is explained by the error terms, which is RSS. So R squared is equal to ESS over TSS. Of course, it's using 1 minus RSS over TSS. So we know the range of R squared is so we say that the higher R squared, the closer the estimated regression equation fits the sample data. Okay, and we call this one the goodness of fit measures. So R squared is the goodness of fit measure. Okay, and let's see some important parts of the R squared. And I don't know this one. Since we know that OLS will select the coefficient estimates that minimize the RSS. So OLS estimator will provide the largest possible R squared given the linear. Okay, that's why we wanted to learn the coefficient of determination. Okay, and we know that R squared is between 0 and 1. Theoretically, it can be 0 or 1, but practically, usually it's between 0 and 1. And there's several points I have to mention is higher R squared. Oh, this one, this variable does not necessarily imply the changes in X leads to change in the Y. Why? Because there may be an underlying hidden variable. When we say hidden variable, it means that X variable doesn't show in the model. Okay? The underlying hidden variables, those changes, leads to change in both X and Y simultaneously. Therefore, higher R squared doesn't necessarily imply the change in X leads to the change in Y. That's what we're saying in this way. Okay? And R squared can very close to 1. Okay? If we have the R squared really close to 1, it is you have to view it with suspicion. Why? Because they are very likely to not explain the movements of the dependent variable Y in terms of the causal effect. Even though they explain their empirical. Okay, this means that there's no causal effect saying if you have higher R squared. And theoretically, we can have R squared equal to 1, means perfect fit. If we have the R squared equal to 1, what's the implication of that? This implies that no estimation is required, and the relationship is completely deterministic. It's already determined, and the slope and the intercept can be calculated from the coordinates of any 2 points. So we don't have to do the OLS estimation, in other words, because this perfect match. Perfect relationship is already decided. Okay, and theoretically, R squared can be 0 too, if we have the ESS equal to 0, right? So the R squared, when ESS equal to 0, 1 minus ESS over TSS. When ESS equal to 0, then R squared is 0. Okay? So if R squared near 0 shows failure of the estimated regression equation to explain the variation of y, better than could be explained by sample mean. So if we don't have any estimation or estimators, the best way we're using y bar. But if we have some estimator like OFS, we will get the R squared, which must be, greater than 0, because with the OLS, we can have this estimated regression, which is different from just y bar. Okay, it will depend on different values of x, and we can expect the y hat instead of just y bar. Okay, this is what I'm trying to say. Okay, then last week, some students asked us that how high the R squared. Okay, so this one will say there's no simple method to determine how high R squared must be for the fit to be considered satisfactory. Okay, because depends on the data. Okay, if it is time series data, we often get very high R squared. So because those time series data are both x and y are significant with the time trends. But for in cross-sectional data, which is measure the same point in time, but different units, right? Different subjects. Therefore, the cross-sectional data, we often get low R squared, because those observations and the subjects are different in ways that are not easily quantified. Okay, and there's no measure is perfect. We do see some problems with the R squared. So the major problem with R squared is that as long as you adding another independent variable to the particular equation, R squared can never decrease. In other words, if you add one more, which is nonsense variable, into the x variable, although if we do the research, we won't add the nonsense variables in it. But that's why I'm saying that if we add one more variable, which is very little impact on the y, even in that case, the R squared will increase, the amount of increment is very small, but they will never, get a decrease. Therefore, we're not able to identify which variable is important to affect the variation of the y. Okay? So with this consideration, we'll make another similar coefficient of determination. We call it adjusted coefficient of determination. So the definition is like this one, and not only the R squared, we put the bar here, that we say this is adjusted coefficients. Okay, and the formula is this one. And how is this related to the original R squared? Let's see whether I can here. R squared, then we say that is ESS divided by TSS, which is also equal to 1 minus RSS divided by TSS, right? Nobody have any problem with this one, right? Okay, and now I'm going to compare this expression, since this is the original r squared. But adjusted r squared, okay, is equal to 1 minus 1. R squared, RSS, again, is RSS and TSS. But I have to divide it. What we call this is degrees of freedom, both on the numerator and denominator. Okay, for the TSS means the total variation of the y. How many observations do we have? If we have n, like the expression here, if we have n sample size, okay, so how many n do we have for our homework? Okay, today's homework. How many n do we have? Everybody notice that? How many observations do we have? For grading examples, how many samples do we have? Okay, look at page 46 on the textbook. Our table 1.2 is the original data. This is the original data, right? How many observations do we have? 25, right? So n is 25. And since TSS is the variation of the y, when we have the regressions, both y and x variable should have the same observation, right? Those with also y and x have been included as the data to do the regression analysis, right? Either one of them missing, cannot include it as the data. Okay, so since the TSS is the variation of the y variables, and we have for example, the rating data, we have 25 observations. So n is equal to 25. Okay, then this one is n minus 1. So means using 25 minus 1. So equal to 24. This is the 1 minus 10. Okay, how about in the numerator? This one says n minus k minus 1. What does this k mean? K means the number of x variables. K is the number of x variables. So for our assignments, what's the k? How many variables do we have for x? 2. One is hard, the other one is easy, right? So k is 2. So again, this one is 25 minus 2 minus 1. So what is this equal to? This one is 22, right? Okay, look at the two expressions. Look at the two expressions. Okay, I have this one is RSS over TSS. And what does this look like? If I'm using this data, it turned out to be 1 minus RSS divided by 23 over TSS divided by 24, right? So how does this math go? 1 minus RSS divided by TSS, then 24 over 22, right? In math. Understand what I'm saying here? So how do you compare these two? Which one is higher? The number is bigger. This 1 minus RSS over TSS. This one is 1 minus RSS over TSS. Multiply this factor, which is greater than 1, right? So adjust the R square will become smaller. So it was the same data set. The adjusted R squared is always smaller than R squared. Okay? And why do we adjust these degrees of freedom? This is, what's the difference between the numerator and denominator? I mean, this degrees of freedom. What does this what's the difference between these two? One is n minus k minus 1. The other one is 1, n minus 1. So the difference is k, right? Means the more x variables, then you minus more x variables, the number of x variables. Therefore, this one is 22. If we have 2 variables, therefore we have 22. If we have 10 variables, then what's the number of this one? 10 variables, then it comes to 13, right? If I have 10 variables, 25 minus 0 is 14, right? So it comes 14. So if I have this one 14 here, what's the adjusted R squared? It's getting smaller. In other words, if you add more x variables, especially when all these x variables is not important, then you adjust the R squared. It's getting less and less and less. So the more variables included in the equations, the adjusted R squared will getting smaller. However, the original R squared isn't affected by what kind of number of the x variable, isn't it? So you see the difference? Therefore, we need an adjusted R squared to replace or overcome the problems of R squared, original R squared. You see the point? So that's the adjusted R squared form. So this is what we say that adjusted R squared measures the percentage of the variation of y around its mean. That's explained by the regression equation, adjusted for degrees of freedom. And wording is always hard to understand it. But after I do the expression like this one, then you can understand the meaning of those words, right? Any questions about this? Is that adjusted R squared really counts the number of x variables. Okay, and this is what we really want. Okay, so that's why I'm saying that an increase in adjusted R squared indicates that the marginal benefit of adding a variable exceeds the cost, while a decrease in adjusted R squared indicates that the marginal cost exceeds the benefit. When we say that when you marginal effect of adding a variable is what? Means those x variables which can explain more. Now, if it is important factors, if we included this important factors into the regressions, then we can get more benefit than cost. Okay, cost. Add one more variable is the cost because it will reduce the degrees of freedom and get the R, just the R squared. It's even smaller. However, if this is important variables, even I counted this cost, then my just the R squared, get more benefit because we added one more important variable. Does that make sense? Okay, and one thing I have to mention that R squared is always between 0 and 1. Okay, but adjusted R squared, it can be negative. But as large as one, it will not exceed one. Okay, but it can be negative when your variable, you have larger, you have a lot of not important x zero. Then adjusted R squared can be negative. Okay? All right? Okay, one thing I will also like to mention that no matter it's R squared or adjusted R squared, both of them can be compared. The differential equation with the same degrees of same dependent variable and different number of independent variable. What does that mean? If I want to compare two models, okay, and these two models, I need to have same y variable with these two models, but it can be different x variables. For example, one is two x variable, the other one is 3x variable. Okay, I wanted to compare which one is better. So we're using the notation, by using the definition, we know that the higher R squared, the better. Okay, so if we compare these two models with same y variables, but different x variables, the one with higher adjusted R squared is better. You know what I'm saying? So when you compare two models, the y variable should be the same. What do we mean by the y variable is the same? Okay, we mean, same measurement units. Okay, I cannot compare the one, okay, look at this one. Adjust R squared and R squared not as useful when comparing the fit of two equations that have different dependent variables. Okay, or the different variables are measured differently. Measured differently. I don't mean use the different measurements. Just defining it differently. Okay, that means these two dependent variables. These are not the same dependent variable. Okay? Okay. I think this is one last question is the qualitative fit of an estimated equation is only one measure of the overall quality of the regression. So not just use only adjusted R squared to measure the overall quality of the regression. We consider that as one of the measurements. Okay, one of the measurements. Okay, and the degree to which the estimated coefficient conform to economic theory and also the researcher's previous expectation. Also, those coefficients are just important as the fit itself. I mean, your common sense, your experience, your theoretical foundation about the relationship with x and y is equally important than just using one measure like R squared or just R squared. This is what I'm trying to say. All right? Okay, so this is the 2.4, about the 2.4. So I finished 2.4. Any questions? Okay, if we don't have any questions, the last section of this chapter 2 is one of the examples. Okay, this is Look at example from the textbook, page 73. We have one example. Okay, this is about the some of the cheese from mozzarella cheese. I love mozzarella cheese. Do you? No, I love it very much. Okay, so this white variables is mozzarella, which is the U.S. per capita consumption of the mozzarella cheese in pounds in year 2. Okay, then we use two variables. One is income, so this is U.S. real disposal per capita income, and which in thousand, the measurement units is $1,000 in year 2. And the second X variable is what? Drowning. What do you mean by drowning? The U.S. debt due to drowning after falling out of a fishing boat in year 2. Tell me, there any sense that you will include X2 into this regression model? Have some relationship with the consumption of mozzarella? Not at all, right? Okay, so the book shows the examples which we have two equations. One is 2.16. Okay, this sample size is only 10. And look at this one, 2.16. Okay, the red, I use the red one, okay? This is using just income as an X variable, okay? Then the second one, 2.17. I'm using another one, which called rounding. Doesn't make any sense. It's insane. Doesn't make any sense, okay? And of course, although we don't have data, but the author shows that if we have to use income as an X variables, and look at the adjusted R square, which is what? 0.88. Okay? 0.88. And equation 2.17 is adding one more variable, which is drowning. Okay? Then it turned out to be the adjusted R square is increased for 10%, almost 10%, 9%. Right? So if you are the researcher, okay, which model you are going to use? Is that this question? Which one you're going to choose?
First one, right?
Yeah, so equation is 16, right? Although it is lower, just that square. So what I'm saying is the moral of this story is, adjust R square, although the adjusted R square is the best, is the good measure of goodness of things. However, in this example, according to the theory, the drawing doesn't make any sense. Include it in one. Yes.
So actually, econometrics are not the proof of, I would say, real life correlation between variables, right?
Yes.
Because, I was reading in the position that, like scientists often, when they want to prove their point so much, even though they are sure they're going to be right, they use econometrics to prove that, the statistics show that I'm right, even though the theory is wrong, right? So
Yeah.
there's a lot of, even in the scientific world, misuse of type of statistical models.
So always starting with theory. Always starting with theory. I mean, do not just use your, guessing. Okay, like this one, in theoretically, we never put drawing as important variable.
So can we say that the legitimacy of correlation between variables is only due to the coherence of the, how would you say, underlying theory?
Well,
Is that the theory that behind the statistical models has to be very coherent and well thought, because it's not, you can prove, statistically speaking, things that could be wrong and false.
yeah,
That is it.
the econometric and also we say the regression analysis is always based on the theory. Okay, do not just use all this data and statistical, you prove some relationship, then say it is, there's a relationship with the X and Y. Do not do that. That's not important. That's not correct. We always started with the theoretical parts. We always started with the economic theory. Okay, so how do you know those theories? It's from the article we're reading, from the studies. You know, if you want to study something, some topic, read the articles related to this study, and you'll find a relationship with the X and Y. Do not just using something out of your mind, then run the regressions, and then say, oh, statistical important. Then you say the result is correct. No, never do that. Never do that. Because we always say that before you run the data, always thinking the field, the related field, and always thinking the relationship, and thinking about the expected directions of the X and Y. We're not saying those regression results based on the estimation. We collect the data, we estimate using the computers, and now after you collect the data using the computers, it's easy to get output. But this is not what you base on to say the result. Okay, the result is originally based on the economic theory first, then set up the regression models, then collect the data, then estimate it. So what do you see? The estimation is to check the theoretical relationship between X and Y. Instead of come out with the new creation of what you did. Do I answer your questions?
It wasn't a new question, it was like more like intelligence. It wasn't a new question, it was like more about an observation. I just observed the fact that Mish did and prove your points in the way that it's not actually technically correct.
Yeah, okay. Now from chapter 3, we are going to talk about how, in practical way, that those professional researchers doing their regression analysis, what step you have to follow in order to do a correct or a good research. This is like chapter 1 and chapter 3, chapter 2, we're just starting to just telling you that a regression analysis is a technique. Okay, then from chapter 3, we started to teach you how to learn how to do the regression analysis in practical way. In other words, working with your own thesis. To be graduated after 2 years, you need to follow all these steps. And with all these procedures or all these steps, then you can can help you to finish your business and also save your time in order to have a good result. Okay, so far we didn't really say something about the theory. Okay, but after that, since we're not talking about some kind of study, therefore, we don't have any really some theories, economic theories, to tell you that what X variables and Y variables. But whatever we use the example in this class or in this club, okay, we are always assume that we already check with the theory. Okay, we already checked the theory, and the theory told us that this is what we have to do with the X variables. And in order to do these studies, I have to collect this Y variable, then X variable. Okay, so in your other subjects like marketing or in human resources or something production management or something else, human behavior in that area, then you will know those articles and you will know what kind of theories inside that study, and you know what's the Y variable you have to choose, you know X variables. But in this class, we'll just tell you those statistical tools that you can use, those theoretical the subjects which you can do in your research. Okay? All right. So this example shows that with 2.17 is the one with nonsense X variables, but we get a higher adjusted R squared. So even we get a higher adjusted R squared, we'll never say equation 2.17 is better than 2.16. Based on the theory, 2.16 is good enough. Okay? All right, so do not just, so this is why we use the topic say, misuse adjusted R squared. Do not always just compare the higher the adjusted R squared, the better. No. No, never do. Okay? All right. Then, so this is what I'm trying to say, that no single rule of econometric estimation is likely to work in all cases. Instead, a combination of technical competence, theoretical judgment, and common sense makes for a good econometrician. We do need technical competence. We need theoretical judgment, also your common sense. Okay, I think most of the theories is coming from common sense. Started with common sense. Okay, something else. The management of overall part, the regression model of the overall fitness adjusted R square, and the degree to which the estimated coefficient conform to economic theory and expectations, which means developed by the research before the data was collected. Okay, so this is, and I put this threatening, all this you have to think about before you collect the data. Not collect the data, then do the output, do the estimation, and see from the output. That's wrong. That's really reverse, or we can say this upside down. Right? So this is what I'm talking about for the chapter 2. Okay? So any questions about it? Any questions? Okay, if you don't have any questions, Maybe that's for today. Okay? Let's see what we, I want to talk about chapter 3. So we're going to review chapter 3. Okay? All right. That's for today. Thank you very much. Start the recording.